So what is, we've got this function theta is equal to 9t squared minus 2t cubed radians. Yeah. So A, velocity is equal to d, just for completeness, and that is 18t 6t squared radians per second. And then we just put the numbers in. So when t equals 1, v equals, and actually I ought to really point this out, for angular velocity we should be talking about omega. I won't worry about that in the exam. If you use v for velocity, I won't really worry too much. All right, it's 18 minus 6 times 1 squared radians per second equals 12 radians per second. Yeah. How do we find the acceleration I? So we find don't we? Yeah. Which is (18) minus 12t radians per second squared. When t is equal to 1, I is equal to 18 minus 12 equals 6 radians per second squared. B, when I is equal to 0, we want to find when the acceleration is equal to 0, so we set this function to 0. 0 is equal to 18 minus 12t. Yeah, so 12t is equal to 18. T equals 18 over 12. It's 1.5 seconds. Okay? And that's a pretty good and typical exam question. Might be extended a little bit further, possibly. Okay, but it's not untypical of something you might get. Yes. Yeah, but we're going to do some extended topics after you've done the assignment. That will be the subject of the exam, but it might include something like that. Right? So, on to just will determine whether it's a minimum point or a maximum. We can also have a turning point where the gradient either side of it is the same, called a point of inflection. The gradient before here and after that point of inflection is negative. The grade before and after this point of inflection, both of them are positive. So if we find a turning point and then look either side and find that the gradient either side of that point is either both negative or both positive, then we have a point of inflection. Okay. So, procedure for distinguishing between turning points. First, find the x and y values at the turning point. So, given that we've got a function for y, we determine the first differential. And then we let that differential equal 0 because we're looking for what the values of x and y are when the 0, and solve for values of x. There may be one, of course, and y axis values. One turning point, might be 2 or 3. I might be. We know we're not interested in. They involve negative. Might be more. Substitute the values of x into the original equation y of x. Find the y coordinate value. Or find x and y values of each turning point, TP for short. Of that turning point, whether it's a minimum, a maximum, or an inflection. First of all, we can determine the sum of just before and just after the stationary point. So we put a slightly lower value of x in the function, slightly higher value of x in the differential function, this is, and determine whether they're positive or negative. So what happens is, if the differential goes from positive to negative, either side, then we have a maximum. If it goes from negative to positive, we have a minimum. And if it goes positive to positive or negative to negative, we have a point of inflection. So that's one method. And that's one you can always use. The second option is to differentiate again d2y by dx squared and substitute into it values of x found in part 2 up here. So if the second differential with the value of x is positive, we have a minimum. If the second differential is negative, we have a maximum. If the second differential with those x. Now, sometimes that option is quicker, but remember it does involve you being able to find the second differential. So it involves you a function that is possible to differentiate, and that you have the ability to skill to differentiate a second time. Whereas the first option will always work because you can just put one lower, one slightly lower, one slightly higher x value in the first differential and look at the 2 points either side. Okay, so sometimes this does involve you being able to differentiate the first differential. So let us have a look at an example and look at the two methods. So we've got a function y is equal to x cubed minus 3x plus 5. Find the maximum and minimum values of that curve by examining the gradient on either side of the turning points and by determining the sign of the second derivative. Okay? So how do we start on that? Let's do it together. See some confused faces. So first of all, we're going to do it by the method of examining the gradient on either side. What's the first thing we've got to do? Yeah, y is equal to x cubed minus 3x plus 5. Yeah. What next? dy by dx then, yeah, is equal to 3x squared minus 3. Yeah, everyone agree with that? Seppi, what do we do now? Yeah, but what about finding, just going back to the full process now, we're here. We've found dy by dx. So we've got to let that equal 0. So let dy by dx equal 0. What's the purpose of doing that? Yeah. How do we find out what values of x will solve that? What type of equation is it? Quadratic? Yeah. Sorry? You could have two answers, yeah. Yeah, get to that, Sophie. I'm saying yes. What method have you used to do that? you use? Quadratic equation or... Yeah, but in this case, we've nothing. New x terms. You can have we're not to coordinates. We can equal to 1. We can have x is equal to minus 1. I'll find the value y equals 1 cubed plus 3 times 1 minus, is it? Was on the end plus 5. 1 minus 2 plus 5, so y is equal to 3. That's one turning point. We've got 1, 3. When x is equal to minus 1, y is equal to minus 1 cubed minus 3 times minus 1 plus 5. Minus 1 cubed is minus 1 plus 4 get 4 from plus 3 minus 1 plus 3 is 2 plus 7. Yeah. So we got another turning point at minus 1 times 7. So for turning point 1 at 1, 3, so we've got to choose values of x either side of 1, haven't we? So what would you choose? So this is 0.5 cubed minus 3 times 0.5 plus 5 equals 1.5 cubed minus 3 times 1.5 plus 5 equals result 2. So, first differential, and then we say one, and we find the point at 1, turning point at 1, use a value below, in this case 0.5, and a value of x above. Find the two results for the differential, so we plug the values of x into the differential. We find here that it goes from negative to positive either side of that turning point, and therefore that turning point is a minimum. At minus 1,7, we choose the half and minus 1.5. Be careful here, this one is after the turning point and this one is before the TP. It's going to disappear in a minute anyway. 0.5 and minus 0.5 and minus 1.5, we find that we go from negative, positive to before to negative after, and therefore 1, minus 1,7 is a max. To differentiate the function again, so d2y by dx we get 6x, and then we set x equal to 1, we find out the value of that as positive and it must be a minimum, and when we find out for minus 1 we find it negative, that must be a maximum. So it gives us the same results. In this particular case, that method is quicker. However, should you have to do a turning point finding problem on something where the first differential looks like that, so that ends our kind of revisit of differential calculus. Next week we'll be having a look at integration techniques, and the week after look at some use, and then we'll move on into the new topics for this module. Okay?